Hi and welcome to this video. Today we're going to be talking about ionic radius and in particular how ionic radius compares to the atomic radius for the same atom. So first off, the general pattern is that the radius of a cation is always going to be smaller than that of its parent atom, while the radius of an anion is going to be larger than its parent atom. Now you can see this in this diagram. It might not be that clear to everybody, but if you look at the light blue ones on the left hand side, all the metals, then the blue circle is the radius of the atom, while the dark grey circle in the middle is the radius of the ion. And you can see that those ionic radii are always considerably smaller. Well, not always that much smaller, but always smaller than the radii of the atoms. Whereas if you have a look over on the right hand side, like looking at the nitrogen, oxygen, fluorine, chlorine, etc., then that dark grey around the outside is the radius of the ion, while the lighter grey circle in the middle is actually the radius of the atom. So you can see that they're significantly bigger. So the question, of course, becomes why? And that is what the examiners want you to be able to talk about. The reason is because when an metal atom forms a cation, it's going to lose electrons, obviously. And it always loses those electrons from the outermost orbital, which is almost always an s orbital. That's the first place it goes from, and that s orbital is usually the only orbital in that energy level. So in effect, it's lost an entire energy level. Because the valence electrons are now in a closer in energy level, or electron shell, call it what you will, then that's going to give the atom automatically a much smaller radius. It also then means that the valence electrons are already closer to the nucleus, which means we have a greater attraction, and that's going to pull it even smaller. So let me just quickly show you what I'm talking about. If we consider sodium as an example, okay, sodium has 11 protons. The atom has an electron configuration of 1s2, 2s2, 2p6, 3s1. But when it loses an electron, it then gets an electron configuration of just 1s2, 2s2, 2p6, because it loses one electron. Still has 11 protons, but now the valence electrons are in the 2p orbital, not in the 3s orbital. The 2p orbital is going to be closer to the nucleus, so you're going to get much more attraction between the 11 protons in the nucleus and those valence electrons in the 2p orbital compared to the ones in the 3s orbital, which are no longer there. And that's going to make it smaller. And it's the same for pretty much any cation. And I do recommend when you're answering exam questions about this, that you take the time to actually write out the electron configurations for both the atom and the ion, because that will supplement your discussion. It will give you something that you can actually hang your hat on when you're talking about it. You're not just kind of airy-fairy waffling about, you know, losing energy levels and electrons and stuff. You're actually saying, look, the valence electrons here in the 4s orbital, but the valence electrons here are only in the 2p orbital. The 2p orbital is closer to the nucleus than the 3s orbital, and yada, yada, yada. Okay, so that's cations. Anions are always going to be bigger than the parent atom. And the reason for that, anions obviously have gained electrons, and those electrons are usually going into the same orbital that is already partly filled, usually a partly filled p orbital. The number of protons doesn't change, the number of electron shells doesn't change, but you're putting more electrons into that same shell. Those electrons are repelling each other. When things repel each other, they move further apart. So they are going to move further away from the nucleus, leading to an increased nuclear radius because those valence electrons are then going to be further from the nucleus, you're actually going to have even less attraction between the nucleus and the valence electrons as well. So just to show you what I'm talking about, again, if we consider an atom which forms an anion, let's say we've got oxygen. Oxygen has 8 protons, and its electron configuration is 1s2, 2s2, 2p4. When it forms an ion, it forms O2-, which still has 8 protons. The stuff that you learned in year 10 and 11 hasn't changed at all. And its electron configuration has now become 1s2, 2s2, 2p6. Because those 2 extra electrons that it's gained have gone into those partially filled p orbitals. So the electrons are still in the same orbital, but now you've got 6 electrons in that p orbital instead of 4, so they're going to have greater repulsion, they're going to push each other further away, and therefore the attraction between the valence electrons and the nucleus is going to be weakened, and it's going to have a larger radius. And again, like I said before, when it comes to exam questions, I highly recommend that you take the time to write out the electron configurations and discuss it specifically. Don't just use generalizations, but say this is the electron configuration of oxygen, and when it gains 2 electrons it turns into this, and this is what's happening. Be specific, provide detail. We like detail. Okay, so that's all I want to talk about with respect to ionic radius. In my next video, we will be moving along to other periodic trends, including electronegativity and ionization energy. And I will see you there.